Hi everybody, I'm Prachi.
I'm Uri Gordon.
Hello, I'm John.
And I'm Shannon.
And we are the 404 errors from the Truthful Inchworm Pod.
All right, so in this presentation, we want to tell you about the computational model that we built. But before we get there, a brief interlude about our experience. So I'm sure like all of your projects, we began with a lot of challenges. We took a lot of time discussing, trying to narrow down our question. Once we had our question and figured out what kind of answers we were looking for, we had to figure out what kind of model we want to build and how do we want to code it. We spent some time trying to work in Google Colab, but realized we wanted better version control. So we tried to use GitHub, but some of us had more or less experience. So we took all of these challenges and we discussed them. And we really got some teamwork going. And we realized that the best way to work together on the code was to do some live coding, where one of our really experienced members did all the heavy lifting with the coding while we watched and provided input and asked questions. And we also realized that our project would go much more smoothly and be much more enjoyable if we distributed the tasks.
Okay, so as Shannon mentioned, we oscillated between a lot of different ideas related to the Human Connectome project, but we realized that we're all interested in the motor system. So we decided to focus on motor tasks and decided to pursue the question of decoding task condition from fMRI bold time series. So characterizing a what model so we can figure out whether it was a left-hand motion, right-hand motion, left foot, right foot, or tongue. Our theoretical motivation stemmed from the big modular versus distributed processing debate. So understanding whether there are specific regions that are specialized for certain types of tasks. We decided to characterize the degree of distributed processing across brain regions during task-related activities, specifically motor tasks. And so in this vein, we decided to create 3 separate models using different inputs. So one, fully just motor parcel input, then non-motor region input, and then whole brain activity. So we can characterize this distributed versus modular nature. So the overall flow of our experimentation started with the bold signal. We were interested in a dynamic picture of the brain, so not just a static screenshot of the brain at a time point, but seeing how it changes over time. We did dimensionality reduction and then logistic regression, and from there we decoded the task. So to give you a small insight into our results, you can see here, these are the parcel coefficients across time. So on the x-axis here, you have time, and on the y-axis, you have parcel split by hemisphere. So you can see the canonical finding of, for left hand, you have right hemisphere processing and vice versa. And you can see that in relation to onset of hemodynamic response. And so here, just to give you a bit more insight into this temporal dynamic processing, we just have a visualization of our task specific, so motor regions only, and whole brain across task-related activity. So you can see the difference between the two, and you can see how the parcel coefficients from the logistic regression fluctuate.
So here, each of the images show the coefficients of the logistic regression. They suggest which brain regions and at what times coefficient of the logistic regression focus on to produce its predictions. On the left image, we see that we get 97% when we focus only on the motor areas. On the middle, we see that when we make predictions using the non-motor areas, the accuracy drops to 71%, which is still much better than random, which is supposed to be 20%. But it's worse than the motor area, obviously. That means that the non-motor area carry a lot of information about the task. When we try to use both the motor areas with the non-motor areas, the whole brain, we see results which are comparable to only the specific area, the motor areas. So that means that including the non-motor areas for the predictions didn't improve. So they might not carry extra information to what the motor area does. So assuming we only have fMRI data, which is coarse and low resolution with respect to time and space, and assuming that our models are only linear, we see that the non-motor areas don't contribute to the processing of information in the brain. But that's jumping to conclusion, and more research needs to be done.
All right, so what? Now that we have our descriptive model built and implemented, what does this actually tell us? Well, it gives us a bit of an intuition as to what exactly is going on inside of the brain. It allows us to effectively predict which task is being performed given a certain data set of functional fMRI images from the Human Connectome project specifically. From this, we hope to extend our model's capabilities and perhaps tweak it in a way that would allow us to understand how these brain regions are integrated, perhaps, and also their relative roles and weights for a given task. Doing this might allow us to extend the model's capabilities to other areas such as cognition, higher level mental processing, emotion, these sorts of brain regions, and could perhaps even allow us to predict various types of hemispheric synergies or differences between brain activity. So one of the things that we did was we also decided that we would also like to further understand the relative contribution of signal to noise in our fMRI data. So these are some areas we might explore one day. Thanks.
And of course, all of this would not have been possible without the encouragement and support of our TAs, mentors, and all of the hardworking, dedicated neuroscientists to be. So thank you, and we hope to see you again soon.